หัวข้อ Virtual Test Drive for Autonomous Vehicle Development นะคะจะบรรยายโดยคุณVenkatesulu Reddy นะคะปัจจุบันดำรงตำแหน่งเป็นผู้เชี่ยวชาญอาวุโสทางเทคนิคของบริษัท MSC Software นะคะ
So VTD is a product from Hexagon. So this is originally from various software or simulation technologies, which is acquired by MSC Software in 2017. So then it's become part of MSC Software. So as you know that all, then again MSC Software was acquired by Hexagon. So now it's part of Hexagon. So VTD names for a virtual test drive. Okay, so various team have around 25 plus years of experience on developing this simulation tool and setting the standards for open drive, open scenario, and open CRG. So what are the main challenges we have in autonomous driving? One is a look, think, and act. So for look is mainly with the sensors. Okay, so all the perception sensors is nothing but radar, camera, ultrasonic sensor, LiDAR. So then localization sensors probably might be using IMU or GNS sensors. So then maps, so where to navigate. So you should have a proper maps from point A to point B or from one location to another location. So then interior sensors. So interior sensors is mainly whether it's an occupant sensor or a drowsiness sensor or things like that. So then once you get the data, so then we fuse this data. So then we build an environmental model. So then the localization model, driver model, path planning, driver interaction. So all this fancy features, HMI, and this is where you will have ADAS features for the lane keep assist or advanced cruise control or automatic emergency brake assist and things like that. So then here you'll have all this vehicle motion or driver interactions. So all these cockpits, actuators, and localization things. Okay, this is how the ADAS architecture looks like. So then the middleware, so which is to communicate from one ECU to another ECU or within a ECU to communicate between multi-core processors or the chip and IP. So the customers will have their own IPs for the camera model or radar model. So now let's see that how this can be simulated with a virtual simulation tool in a real time. This is the image video completely simulated in the VTD. This is the clarity of the image you can simulate, completely physics-based rendering. So this is how you could simulate, and you could do even more advanced things with the camera model. Okay, so we have a create, so where you can create all these road networks with our road designer. So then here we have a scenario editor, so where you can pick and drop any of the scenario of traffic participants into the scenario editor. So then we have a presim, so where you can add all the sensors to the ego vehicle, cameras, LiDARs, ideal sensors, ultrasonic sensors. Okay, so physics-based sensors, all those things you can add, then that will perceive the data. So the data you give to your act control, so like driving functions, lane keep assist, AEB, ACC, so all such kind of things. Then you can give back that commands to your ego vehicle or other traffic participants in the traffic scenario editor. So you could create these kind of static environments with advanced things. Okay, so then we have again Leica Geosystem, so that's also part of Hexagon. We have one device from them that's called Leica Pegasus, which will be which you can use it for the entire road scanning. Okay, and then you can bring that road scanning data into the virtual simulation. Okay, with the help of our road factory or road designer tools. Okay, so then this is how you could create the road network, and you can add all the traffic rules and infrastructure things. And once you create a road network open drive, so you could preview that a open drive thing, so how it will look like in the simulation. So we support for OpenStreetMap. Even now with the latest tool, we support for point cloud data also with in hexagon format and OpenDrive and OpenCRG. And then we have a huge set of country-specific database. So here you have a realistic driver, so you can model your driver think parameters also, and we have realistic dynamics, so where you can do the co-simulation with the atoms, okay, and then realistic pedestrians, okay, then weather, so you can do all this kind of wiper things or climatic conditions, so or snow or things, so you can increase the pixel or a raindrop intensity, so all such kind of things you can do. So then we have a number of 3D models and scenarios. Okay, so you could do this parking assistance things, and 3D models consist of mesh texture. You could do change the materials on fly and dynamics, parameter sets, and all those things. And dynamic environment. So once you create a static environment, so then you have to drag and drop all these parameters on this road network, and then you should be able to set the maneuvering to that. So on which direction the vehicle has to go, which path the vehicle has to follow, or even for the same, for the traffic participants also, you could change. So where the traffic participants has to move, and all these traffic lights you can control. Okay, you could do automation also with all these things. So then all these controllers, how you could connect with the third-party vehicle dynamics, and how you could do the animation within our VTD image generator. So this is the flow. Okay, so you could have controllers and you can have vehicle dynamics with the MSC vehicle dynamics. Okay, so atoms basically. So then you could visualize all those things in the graphics. Okay, so the perception algorithms basically. So what is for the perception algorithm, data is very important, the sensor data. So here we have pixel information, the intensity or the RGB coordinates. So physics-based sensors, you could create a fisheye cameras or any other pinhole cameras also. Okay, so and this is the physics-based view, and how the radar looks like. Okay, so the radar FFT based millimeter wave radar. So all these are peak point detections. Okay, and we have all these simplified sensors. Okay, so the ideal sensors which will you can retrieve the data and you can give this data for your control algorithms. Okay, so this is again the cluster list information. So another version of radar. Okay, which will give you the cluster detections. Okay, so then this is how the pinhole camera looks, and a fisheye camera, and this is how you could introduce the noise to the pixels. Okay, so we could see a lot of cases, so many cases where we say that the noise is more on the image, and we could not able to artifact that noise or filter the noise. So you could introduce more noise, and you can implement or improve your algorithms. So this is a lens failure, the chromatic aberration. And this is a YUV pattern, that's another. So the RCC, so you could combine different kind of patterns, and you can do the 12-bit or 24-bit depth, or 18-bit or 10-bit depth. Okay, so this is one more thing. So the headlamp simulation. Okay, you could see that all different kind of headlamp effects. So for the high beam and things like, so you could see only we can focus it here, or when the vehicle is coming in an opposite direction, so you can go to the different mode of lighting. Okay, so you could visualize in a different view in the RGB spectrum format. So all this, all physics-based effects. Okay, so you could use this VTD even used for the visual evolution and the virtual rating of the lights, and the for the virtual testing for the sill and hill. You can get the light formats from like companies called Hella, SRM, or similar kind of companies, and you can import that IES luminous pixel intensity on the headlamp. Okay, so then according to that light format which you get from the customer, so the lighting emulation happens at the same pattern in the VTD. So that's the one more advantage you'll get, and you can do the rating of that lights. So you can get the format from the different vendors, and you can do the rating, and you can choose whichever the lighting simulation or the lights fits for your requirements. Okay, so how we do that? So we use all this HDR monitor and the light source data by the customer. So this is the data format. You can get it from the customer, and you can import in the VTD. We have a tool called Light Source Combiner, so where you can go and import any format, okay, the format which is supported, then that will be applied on the image generator. So this is how the tool looks like. So for the lighting simulation, so then you could visualize all those things in the VTD image generator. So you can have left and right lights, or you can add more also. You can add LED lights. You can combine multiple LED lights into the single source or multiple sources. Okay, so this is the thing. So how to create and the procedure, how to do that. Okay, so then image projection. So you can project the things on street also. If you see recently, the Continental Osram has introduced this kind of lighting mechanism. So where you could project through the lights on the road for the stop signal or this payment sign, velocities, or the traffic conditions, different things. Okay, so this is another LiDAR simulation in the RGB spectrum format. You could see this is with the low resolution and the high resolution. So how the point cloud data has been generated. You could do advanced or highly complex point cloud things with the LiDAR. Okay, so then this is a physics-based thing. So what are the parameters we consider for the physics-based ray tracing? Okay, so all this BRDF methodology and standard parameters to do that, and you can implement your own shaders to implement it. So this one also with the ray tracing. So then how this signal intensity has been reflected on the RGB pair pattern based on the material effects. Okay, so this is the kind of things which parameters we consider. And you could see that, so the difference between the physics-based and the basic OpenGL thing. So if you see the same image rendered, so this also on this both the same image. So here you could see that the door and the metals have been very clearly detected or rendered with the physics-based simulation. So here also you could see that there is a bus stop. So here you see how in physics-based sensors it has been visible and the reflections. So here also it is same. You could see here windows and all is not that much appeared. You could see here all these windows and everything has been appeared very well in the physics-based simulation. So that's where the physics-based is very helpful to retrieve all the points of the reflections or the intersections of these material properties. And this is a radar, physics-based radar. So we use FFT or Doppler Weave or FMCW principle to do the physics-based radar simulation. So where you can get all the hit points or the peak point detections, so which you can give it to the next signal processing algorithms. So you can use the VTD or the different phases or the multiple teams. You can use VTD for the autonomous driving or for the V2X and the ADAS, lighting, homologation. And at the same time, you can use VTD for the MATLAB or software in the loop or SIL or virtual ECUs. You can use for the SIL and the hardware in the loop, driving simulator, and you can use it in the vehicle in the loop also. Okay, so this is how you can think of. So here I'll explain. So when we talk about model in the loop and software in the loop, so all these components comes from the VTD. Okay, when you talk about driver in the loop, so the physical driver is present. Okay, the physical driver is present, and the dynamics, sensors, system, traffic, everything can be simulated in the VTD. So, and vehicle in the loop. So here in the vehicle in the loop, so driver is presented and the dynamics also is coming from the vehicle, and the sensors you can use. Suppose if this vehicle has been mounted with the radar and camera, you can use camera from this real environment, and the radar you can simulate at the VTD. And the systems also same. Maybe for the camera you have a separate ECU over here, and for the radar you can simulate in the VTD. The same with traffic also. So you can have a pedestrian on the real environment, and then you can add the vehicles or other things in the VTD. So hardware in the loop. Hardware in the loop also same. Driver comes from the VTD, and dynamics. So sensors you can have combination. So systems, anyway we have a hardware. Okay, so this is what the hardware in the loop system looks like. Okay, you can use a monitor in the loop, or you can use camera rod at a hill. Okay, you can use radar rod at a hill and things. And this is a ZIL environment. So here we have for the camera, if you look at, so here you have a real scene, and this is how the CMOS thing happens in the real time. Then you have ISP, okay, and computer vision algorithms. In the VTD also, you can simulate the same thing. Here you have a simulation scene, okay, and camera calibration you can do with the VTD. We have a lens design and lens shading tool, and the image sensor tuning. So where you have a camera settings, you could do all those things with our image sensor tuning, and the ISP. Okay, you could do the ISP also. Then you can get the raw data, which you can give it to your computer vision algorithms, which will start detecting the things in the scene. And for the radar, okay, radar also same. So here you have a radar front end, that is an antenna things. You can give those parameters in the VTD. So then in the VTD, so this is called millimeter wave radar. So which can give you the 3D FFT data, or you can improve for the 4D also. So then we have another radar, that's a target list radar in the VTD. You can subscribe the data or the clustered list also. And at the same time, we have a perfect sensor, that's the ideal sensor, which will give you the object data. So based on your complexity or the requirement, you can use any sensor models. Okay, so then hardware in the loop. So we take the different approach in doing the fusion. So there are different methods. So this is one of the methods. So I'll show you the picture over here, the next slide. Okay, so then how W architecture, electrical and electronic things have been implemented in the VTD. So you have camera, where you can do the complete camera simulation with the ISP in the VTD, and a radar. You can do all the radar parameters in the VTD, and you can get the millimeter wave radar output, and a LiDAR also. You could do the spinning and flash LiDAR things together in the VTD, so you can get the point cloud data or the intensity also. Then for the ultrasonic sensor, we have a single ray and multi-ray sensors, which you can use. So you get the ultrasonic sensor, and the GPS, so with the GNSS simulator. Okay, so this is one more thing for the fusion hill. Okay, so you could use VTD for the monitor hill, or at the same time for the radar also, where you can inject the objects, and for the ultrasonics also, and you could do the fusion algorithms or the validation. And for the camera raw data hill, you can simulate the raw data, okay, and you can give it to the FPGA board, and you can use your ECU like NVIDIA or even Mobileye ECU, all such kind of things you can validate. Okay, so this is a driver in the loop. Okay, so you could have different kind of driver in the loop simulations. So VTD will work across different platforms, supports. And a vehicle in the loop, so you can use a head tracker to see the VTD weave, and you can drive on this road. And for the test and validation, so we use different approaches for the test and validation. You can use Python as a test framework to do the automation with the VTD, and as well as we have some partnership or things to do this requirements, test plan, scenario creation, KPIs, test run, and results. Okay, so it will take more time to do manually, but with some tools in the market, we could do faster. So we have partnership with TPT. So that's from the Pike Tech, and another thing is ECU test. So these simulation tools or the test tools will help you to do the automation a bit much easier than manual validation. Okay, so then VTD supports for a cloud also. So VTD has been deployed on the AWS and Azure, where you can create a number of scenarios in parallel. Okay, so and all of them you can validate at the same time. So we support for CI/CD integration also to do all those things. So it supports for all those open standards: Kubernetes, Docker, Spark, Jupyter, and Hadoop. So we use all these open source based and open standard things. So then we support for the co-simulation in the cloud also. You can use MATLAB, you can use a robotic operating system, you can use your third-party software in the loop frameworks. So all those things. So you can, we call that as a sidecar over here. You can validate your driving functions over here. And you can store each and every frame, and you can validate, and you can apply the analytics on that. Okay, so you could do all these kind of analytics on the cloud. We have nice GUI tools which will help you to visualize or analyze do the repetition of the testing and do automation of this CI/CD and automatic triggering of the test cases and results. Okay, so the PTD has been used several customers. So I've picked up a few major customers. So VW is one of our customers. It's been using VTD from decades, okay, several decades. So they use VTD for all things, for the scenario creation, for this integration with the ADTF, or validating the sensor models and driving functions, and realizing their test frameworks and all those things. So then at the same time, so we use, there's one more VANETs, which has been used, which has been used for a vehicle to vehicle communication, or vehicle to X, I mean the V2X communication with the Sumo integration. And AVL also uses VTD to do this drive cube or driver in the loop validation and all. So BMW uses VTD mainly for the physics-based sensor simulation, LiDAR or radar or weather simulations or camera simulations. So this is also for the perception. You can use VTD, and the localization sensors are Novotel, and for the maps, like geosystems. For the dynamics, Adams. Yeah, that's it. Thanks. Thank you for your time.